This video, we are gonna talking about the Hasse diagram and how to use the Hasse diagram to visualize a pose set. And then we're gonna use the Hasse diagram to introduce two pairwisely defined concepts that are maximal and minimal, maximum and minimum. So first of all, let's recall the definition of a pose set together. So a pose set that is reflexive, antisymmetric, and transitive. So those are the three highly important properties when we actually draw the Hasse diagram that will be used. Okay, so here I have written down the brief definition of the Hasse diagram. Well, generally, the Hasse diagram is just a technique for us to use to visualize the pose set. So let's step into some specific example together. Let's consider this example. If the set A has all these elements, and R is a divide relation on A, such that R equals to xy on A, that x divides y. So this is the set theory notation of the pose set. So firstly, let's recall a way to represent a relation on Rosen section 9.3 that we can write down an element, the element in the set A in a circle. For example, if we write A, B in this way, so this is called the node. And then we can use a line with an arrow on it to denote A relate to B. This is called an edge. Okay, so we can use the same way when we actually drawing the Hasse diagram. So firstly, let's recap the definition of a pose set or the properties of it that are reflexive, antisymmetric, and transitive. And we're going to go through these three properties of a pose set to see how well these properties help us to construct the Hasse diagram. Okay, so what the reflexive tells us? Well, the reflexive is saying every element in A actually relates to X. So each of the elements that are related to itself, namely saying each element X in A, X divides X. So we can draw like a looping circle on each node. Okay, here we go. And then, what is the antisymmetry telling us? Well, the antisymmetry is saying for all xy in A, x relate to y and y relate to x implies x is exactly the y. So that is saying there are no two distinct elements in set A that are related to each other symmetrically. Well, it actually not help us that it will be performed on the Hasse diagram, but it's highly important when we go through the following steps. Okay then, let's continue on drawing the Hasse diagram. That is x divides y. So we start with the 2. 2 divides 4. 2 divides 4. 2 divides 8. 2 divides 12. 2 divides 24. 3 divides 12. 3 divides 24. 4 divides 8. 4 divides 12, 4 divides 24, 7 only divides 35, 8 divides 24, and 12 divides 24. Well, 24 and 35 divides nothing within the set. So here we go. Well, consider this diagram that we draw. It's kind of a mess, and it did not help us to better visualize the pose set. Well, let's just stop right here and back to the property of a pose set. So what is transitive actually tells us? Feel free to pause the video and think about it yourself. How could the transitivity help us to better construct the Hasse diagram? Well, the transitivity actually tells us two implicit conditions. That is, firstly, when we actually use it like a node and an edge, perform a transitivity, that is A related to B and B related to C, it's vacuously saying that A related to C. However, when we perform in this way, this edge is kind of useless, since if we can go from A to B and from B to C, then it's vacuously saying that we can go from A to C through B. So then we can just get rid of this useless edge and just leave it as this simplistic form. So back to this problem, we can get rid of all the duplicated ways that that shows for a transitivity. Well, we can also get rid of all the loopings on each of the nodes, since a poster that is vacuously reflexive, so each element that is always related to itself. So here, this is more simply a form, but recall there's an interesting observation that when we actually draw in the phase diagram, we always started with the least element in the set and go upwardly with the absolute value of the element in the set A increased. So that is saying, is there a better way for us to draw the diagram that is vacuously shown that the relatively smaller elements are at the bottom and we go upwardly, then the relatively larger numbers are at the top? So that is also a second implicit condition that the transitivity tells us, that if A is related to B and B related to C in a partially ordered relation, and this then implies A related to C. So in this way, A is a relatively smaller number, and combined with a specific operation that is a partially ordered relation, and B related to C and A related to C. So it's typically saying that A is smaller than B and B is smaller than C in this way. Okay, so here we are. This is the simplest final version of my Hasse diagram. So that is saying, all the relatively smaller number are at the bottom, and we get rid of all the arrows here just to draw the Hasse diagram in the simplest form that could help us to visualize the posset. So we go upwardly, and then we get rid of all the loopings previously, since it's just the present, and we also get rid of all the duplicated arrows at the edge when we're talking about the transitivity. So here's the final version. And then look at this Hasse diagram. I'm going to use this to introduce two pairwisely defined concepts that are maximal and minimal. So here I have write down some simple notations for the two pairwisely defined concepts. Well, the maximal, that is, if A is a maximal in the posset, if A is maximal in a posset, S less than or equal to, if there is no B in C, in S, such that A less than B or A related to B. And similarly, an element of a posset is called minimal if it is not greater than any element of the posset. That is, A is minimal if there is no B in S such that B related to A. Oops. So maximal and minimal elements are easy to spot using Hasse diagram. They are the top and the bottom element in the diagram. So for this question, the 2, 3, and 7 are all the minimal elements, while the 24 and 35 are both the maximal element. So that is saying a poset can have more than one maximal element and more than one minimum element. That is saying two of them can greater than or equal to one element. Okay, so compare with the maximum and minimum element, we're going to talk about the maximum and minimum, also called the greatest element and least element. So we call A is the greatest element of the poset S, less than or equal to if there's a B in the set such that B is related to A for all B in S. And the least element, and we call the A is the least element or the minimum, that is A is in S less than or equal to if for all B in S, A is related to B. Okay, so one of the highest important fact about the minimum and maximum, that is both the least element and the greatest element, is unique when it exists. So that is very highly important. So consider this problem back. There's no maximum and minimum, since if we say the 2 is a minimum, but the 35, since the two of the parts are separated, so we cannot find a minimum element that is related to any rest of the element in the poset. Also, the 7 is separated from the main part, so 7 is not related to any other element within the set except 35. So feel free to pause the video again to see whether you could find a good example to show that that is a poset that has both the minimum and maximum simultaneously. So here we go. So this video we talked about how to draw a Hasse diagram and use the Hasse diagram to visualize the maximum and minimum. Thank you.